All right, now we are ready to solve our system of equations, and the process is going to look pretty familiar to most of us. We do what we always do when we have a system of equations, which is to use one equation to isolate one of the unknown variables so that we can replace that variable in the other equations in the system. In this case, that would leave us with one equation and one unknown in our second equation, which means that we would be able to solve for our temperatures in terms of known constants like omega, A, and sigma. The one difference here is that when I solve for a temperature, I'm not going to solve the equation completely so that I just have TE or TA alone on one side of the equation. I'm actually going to take advantage of the fact that everywhere in our system of equations, our temperatures are raised to the fourth power and being multiplied by the Boltzmann constant. This allows me to treat the whole expression, sigma t to the fourth, like one of our unknown variables, because I can easily substitute expressions in for sigma t to the fourth in any equation. And it means that I don't have to worry about dividing by sigmas or raising expressions to the 1/4 power in order to isolate t's. Basically, it's a trick that really only makes sense on these climate modeling problems. But it's worth mentioning because it'll save us a lot of ink and paper when we are doing these kinds of problems. So the first thing that I'm going to do is take a look at my steady state equation for the atmosphere stock. And what we will notice here is that the equation is pretty much solved for us already. The term with our Earth surface temperature is already expressed in terms of the atmosphere temperature expression. And we can pretty much go ahead and substitute in for sigma TE to the fourth in our second equation in order to eliminate Earth temperatures from our second equation. In other words, we're going to substitute 2 sigma TA to the fourth for the sigma TE to the fourth that exists in our second equation. This means that we can rewrite our second equation as omega over 4 minus A omega over 4 plus sigma TA to the fourth is equal to 2 sigma TA to the fourth. Next, we can simplify our expression a little bit by subtracting sigma TA to the fourth from both sides to eliminate it from the left-hand side. Now we are in business because now we have isolated sigma TA to the fourth on the right-hand side of the equation, which means that now we have an expression with no unknowns that we could use to substitute back into our original steady state equation for the atmosphere. If we substitute in omega over 4 minus A omega over 4 into our steady state equation for the atmosphere, we can solve for TE purely in terms of known values like omega, A, and sigma. Let's go ahead and do this. With this substitution, we get sigma TE to the fourth is equal to 2 times the expression that we are substituting. Now we have two expressions, one that we could solve for TE and one that we could solve for TA. And if we want to solve for TE, we could divide both sides of the expression by sigma. And we could raise both sides of the equation to the 1/4 power to get rid of the exponent above our temperature. And we would find that TE is equal to 2 over sigma times omega over 4 minus A omega over 4 inside a set of parentheses, all raised to the 1/4 power. If we plug this into Mathematica, we would find that TE is equal to 303.361 degrees Kelvin. In units of Celsius, this is about 30 degrees. And in units of Fahrenheit, this is roughly 90 degrees. So it looks like we're a little on the hot side for a global average surface temperature. We're probably most interested in the temperature of the Earth, but if we wanted, we could also find the temperature of the atmosphere in this model. We could use our expression that isolates TA And like before, we could divide by sigma and raise both sides to the 1/4 power. We would end up with 1 over sigma times omega over 4 minus a omega over 4 inside a set of parentheses, all raised to the 1/4 power. And if we plug this into Mathematica, we'd find that the temperature of the atmosphere is 255.095 degrees Kelvin. Here we're talking negative 18 degrees Celsius, or right around 0 degrees Fahrenheit. Intuitively, it kind of makes sense that the atmosphere is going to be a little bit cooler than the surface of the Earth. The Earth is receiving energy from the sun and the atmosphere. Meanwhile, the atmosphere is only receiving energy from the Earth below.